good evening. We'll start in a few minutes and we'll wait if someone else will also join for the meeting. Okay, then we'll start. So good evening everyone. I am Diljit Datta. I am a PhD research scholar in Indian Institute of Science. So today we'll be having the first problem solving session for the course optimization methods uh, in civil engineering, which is being taught by Rajiv Kumar Bhattacharya. I hope you have attended like first week of lecture and went through the lectures of the class. So I will be today in this session I will be just going through the just brush through the concepts that were being taught, and we will solve some basic problems, because initially first week we don't have any complicated problems. We will be solving some basic questions only, and I hope it will help you clarify your doubts, and if you have any doubts feel free to ask me. So let's get started. First of all, let's see uh, what are the why optimization came into study, like what is the reason. So, and why it is a part of a like very broad phenomenon called operation research. So the operation research is a branch of mathematics which is concerned with the application of scientific methods for decision making and finding an optimal solution. So so there are different methods of operations research. One is like using mathematical programming. Here you can see these are all the methods that uses mathematical programming, or it has simple optimization techniques. And these optimization techniques are based on various methods. We can use calculus, we can use linear programming, we can use dynamic programming. There are also called stochastic programming, separable programming, multi-objective programming. So all these are different methods for optimizing a problem. You have some problem, you want to find the optimal solution. So based on the nature of the problem and the type of the problem, you have to adopt one method. And these are different methods for getting optimized the optimum solution. So this is one way, and we'll go through some of these methods in further weeks of the course. And also I don't think we'll be covering all the methods, we'll be covering only some of the methods. And in recent times also there are other processes like stochastic process techniques also, where we use statistical decision theory or Markov processes. Markov processes are like processes where the decision that has been taken in the future, it doesn't depend on the decisions that are taken in the past, so it is independent. So these type of processes are called Markov processes. So these are also used for making decisions, optimum decisions in some cases. Then there is renewal theory, simulation methods, and reliability theory. These are all advanced concepts. And finally there are some statistical methods. I hope you have heard about machine learning. Machine learning is also a type of optimization problem, optimization. So we have a problem, we want to get an optimum solution for that problem, and machine learning is a type of method. So in machine learning there are methods called cluster analysis, pattern recognition, and also we have discriminant analysis, or PCA, principal component analysis. So these things are covered in machine learning courses. If you are interested, you can attend those courses. And in optimization also there are some recent advancement in optimization methods, and people are trying to explore new methods, new non-classical methods for optimizing our problems. So one few of the such algorithms are genetic algorithms, simulated annealing, and colony optimization, particle solve optimization, neural networks, and fuzzy optimization. So I'll just give a brief overview. So what is genetic algorithm? Genetic algorithm is a method which we try to simulate the genetic method, like where there are chromosomes in DNA, chromosomes in our DNA. So when there is an offspring from two different parents, optimum method is a chromosome is selected based on some algorithm, some like natural algorithm. So we are trying to simulate that algorithm to get solution, like good optimum solutions for our applications, for our real time for our natural processes, like different problems. So this is called genetic algorithm. We will see through details of genetic algorithm in the later weeks, in I think week 9 or 10 in this course. And we'll also try to get some code to try to write a code for solving a problem using genetic algorithm. Then there is simulated annealing. Annealing, I think you have heard. Annealing is a process where it is used to make glass. In glass, what we do, first we heat the glass to very high temperature, and then we cool it very slowly in phase by phase. So this is called the annealing process. And so this method of annealing, that is getting first heating the substance and then cooling it in different steps. So this type of method is also the process that goes inside annealing. So these simulations are also used to solve some other real life problems in different areas. Similarly, ant colony optimization. So when an ant is, you have seen ants, they make ant hill. So the ant hill they make in optimum shape. It's like for their convenience. It is not that ant hills are made in some random shapes. No, it is not like that. They have some method, and people are exploring different ways how we can simulate that ant hill, ant colony optimization for solving our problems, because that is also a very optimum process that is being adopted by nature. Similarly, particle storm optimization is like trying to simulate the optimization methods. Like you can see a beehive. You can see a beehive is always in a like kind of convex kind of shape. It is not in some random shape always, right? So there is some method that they go into that the bees are applying to get that kind of shape, right? So this is also a type of optimization only. So this type of net method is also can be used for solving some problems. Then there are neural networks. Neural networks also comes under machine learning and AI. So it's like we tried. We have a training set. We have then uh, decision variable. We are going to try to find a relation between those two, that training set and the decision variable, and try to get a relationship, and then we'll try to optimize the relation between them by using the methods of neurons. Neurons are, I think you know, neurons are the nerve cells in human body. So these neurons are connected to one another, and they pass information from one neuron to another neuron. So in that way, so this method is applied for solving some problems like very complex problems. And finally, fuzzy optimization. This is also a type of optimization where we don't have definite boundaries. Like we know in most of our problems we know the very determinant kind of values. But in fuzzy optimization, we don't have the like constraints are not discrete. There might be the values might be shifting from one range to another. So in that case, we use a fuzzy optimization. So these are advanced concepts. We will go through some of them in the later part of the course, and some other concepts will be covered in some other higher level courses. Okay. So this was a basic overview of the methods in operational research. So we'll just now see through what has been taught in the first week. So initially, like what is optimization? I think you all know it is the act of obtaining the best result under given circumstances. So how do we what are the basic steps involved in optimization? So first of all, we have to fix a objective function. Like we need to find a function where we have to optimize the solution for that function. So the solution is either like we want to do minimization of the function, or we can do maximization of the function. So based on our necessity, we will adopt one of the method, either minimization or maximization. So that is how we define the objective function, and then we have to fix a decision variable, the variables that will go into the objective function, that will define the objective function. So one is objective function, second is decision variable. So these two things, and thirdly there will be constraints. So it's not like always you just have to find the optimum solution. No, there will be some constraints you need to satisfy for getting the optimum solution. The values of the optimal solution must lie in some range. It must be greater than some values. So this kind of constraints will always be there when you are trying to get an optimum solution. So this and also this objective this optimization, it can be single variable and multivariable. When we have only trying to optimize only for one variable, it is called single variable optimization. If you are doing it for multiple variables, we call it multiple variable optimization. So we will see one by one what this single variable and multivariable. So going into single variable optimization, first we need to define something called stationary points. So what are stationary points? For a continuous and differentiable function f of x, this is very important, that the f function should be continuous and differentiable. A stationary point x star is a point at which the slope of the function is 0, that is f dash x is equal to 0 at x equal to x star. F dash x is the differentiation of the first order derivative of the function. So in case of, there are three types of stationary point. One is the minima, This is the first case, the second is the maxima, and third is the inflection point. So in case of minima, the function value, the derivative, it first decreases and then increases. Second is similarly, it also in case of maxima also, the second derivative of the function will be less than 0, that is the slope will be changing the sign. And third is the inflection point, where the second derivative is 0 but a third derivative will be changing sign. We will see the details again. So when we know there is minima, maxima, there can be global maxima and global minima. Function is said to have a global maxima if at x equal to x star, if f of x star is less than fx, global minima if f of x star is less than equal to fx for all x in the domain where fx is defined. So you can see this figure. In this figure you can see like a1 and a2 are maxima. The function is having the maximum values in those 2 points, and b1 and b2 are the minima. But b1 is the point where the function is the least in the range, that is the domain a to b. So b1 is the global minima of the function. Similarly, a function is said to have a global maxima if f of x star is greater than fx for all x in the domain. So in this case, at a2, the f of x as a2 is greater than all other f of x in all other points. So a2 is the global maxima. Similarly, now what we call the other points, a1 and a3, they are called relative maxima. Similarly, b2 is called the relative minima. As I already told that now optimization problem, it can be constrained or unconstrained, so we have to get the maxima or minima based on some constraints. So in constraint optimization, what we do, it is the method was invented by Lagrange. By the method called introducing Lagrange multipliers. Similarly, in unconstrained optimization, we don't have any constraints. We just have to get the maxima or the minima of the function without any constraints. So the solution of unconstrained optimization was first done by Cauchy, and the method that he developed for getting this unconstrained optimization is called the steepest descent method. Okay. So now we define like what are maxima and minima, how to get. So so the thing is that if for getting an optimal solution, we first need to have a minima, or that is a stationary point in the function. So how the stationary point can be minima or maxima. So how do we get a stationary point, and what are the necessary and sufficient conditions in order to for optimality? So the necessary condition for a point of stationarity is f dash x equal to 0. We have already seen that. And the sufficient condition is that suppose at a point x star, the first derivative is 0, that is f dash x equal to 0, and the first non-zero higher derivative is denoted by n. So if n is odd, then x star is an inflection point. So here f dash x equal to 0 and f double dash x is not equal to 0, but f triple dash x is equal to 0. So here it is or it can be f3, or it can be f5 or f7. So if this derivative is odd, and it is equal to 0, the first odd derivative is 0, then it is called the inflection point. If n is even, that is f double dash x equals to 0, then we can have a local maxima or a local minima. And depending on if f double dash x is greater than 0, we will have minima, and if f double dash x is less than 0, we will have a local maximum. So this is a proof. This is a proof that has been adopted. That has been done for this getting the local minima, that is that f dash x is equal to 0 to get the stationary point. And I think sir has he has taught in the first week, but still I'll just go through it quickly. So the first derivative f of f dash x equal is given by the first principles in this way. That is f star of f of x star plus h minus of f of x star divided by h, where h tends to 0. Now suppose we have a interval. We have a interval a to b. Now in that interval, the relative minima, relative minima or maxima at x equal to x star we have to get. So if x star is a relative minima, then f of x star should be less than or equal to f of x star plus h. So h can be greater than 0 or less than 0. So this is f of x star plus h. This is also f of x star plus h, where h is less than 0, here h is greater than 0. So these 2 points are just, I am magnifying it here. H is tends to 0, h is very near to 0, but it is greater than 0, like it can be greater than or less than 0. So this is f of x equal to x star. So if f of x star is less than equal to f of x star plus h, in that case we will have a relative minima. So for h very close to 0, f of x star plus h minus f of x star by h is greater than equal to 0 for h greater than 0, and f of x star plus h minus f of x star divided by h less than equal to 0 if for h less than 0. Now in that case, so only way is that if you are approaching f of x star in both these options will be satisfied, that is both these conditions will be satisfied only if at the point x star f dash of x star is equal to 0. Similarly, so this is the condition, the necessary condition that we need for getting a optimal solution. Similarly, we can get for relative maxima, we will get the same condition, that is f dash of x star is equal to 0, and this you can derive as your homework. Now we have seen this point for x star that lies in the range a to b, but if x star is this point is at the end point, in that case this theorem doesn't give any information, because we don't have f of x star plus h, we have only value in one side of the value of x star. On the right hand side of x star there is no value. Similarly for this point, so in that case this point can be a maxima, it can be a minima, or it can be a inflection point also. So we won't get any information from this theorem. So this is the limitation of this theorem. And next we see the sufficient conditions for optimality that I already discussed. The sufficient conditions for optimality, it comes from the Taylor series. I hope you know the Taylor series. So it's a way of expanding f of x star plus h is equal to in terms of f of x star. So we'll get this f of x star plus h is equal to f of x star plus h into f dash of x star plus h squared by 2 factorial f double dash of x star plus up to h to the power n by n factorial into f n of x star. So we know that from the necessary condition that f dash of x star is equal to 0, and we assume that, like, suppose we want to generalize the condition, so we assume that till f to derivative to the power f derivative of f to the power n minus 1, all the values are 0. So in that case, what are the terms that remain in the Taylor series? So f of x star plus h minus f of x star is equal to h to the power n by n factorial into f to the power n of x star. Now, if when n is even, h to the power n, it will it doesn't depend on the sign of h, whether h is greater than 0 or less than 0. If n is even, then h to the power n will be greater than equal to 0 for n even. So if this is greater than 0, then f to the power n x star, it will depend on the sign of f of x star plus h minus of f of x star. So if f of x star plus h minus f of x star is positive, it is called the local minima, and if f of x star plus h minus f of x star is negative, it is called the local maximum. So this is, and if n is odd, if now second case is where this is n is even, if n is odd, in that case h to the power n by n factorial, this value will change the sign with the sign of h. So in that case, it is an inflection point. So this is the derivation for sufficient conditions for optimality. So before we proceed, do you have any doubts in the derivation? If you have, you can ask me now, or else I will proceed. Okay, then if there are no doubts, I will proceed. So yeah, this was all about single variable optimization. Now we will see how we can get for multivariate optimization. In multivariate optimization, the problem formulation will be in terms of partial derivatives, because we have, so the objective function, so the objective function will be defined like this, that minimize of f of x, where x is not a single variable, it is a matrix or a array of like n variables. So x is a x is equal to x1 to xn is a matrix of n variables. So in that case, we have to minimize fx or maximize fx. So and constants, so the we are not going to constants now. So the necessary condition will be that partial derivative of x star, that is, we find an optimal point in the region, and that partial derivative of that function of x star with x1 with respect to x2 and with respect to xn, that all the variables is equal to 0. This is the necessary condition. So it is just extending the single variable condition to multiple variables, but when we extend to multiple variables, we are not using the simple derivative, we are using partial derivative, because the function is varying with all the variables. It is not just depending on one variable. In that case, we always have to use partial derivative. So in this multivariate optimization, the sufficient conditions for optimality. So the sufficient condition for optimality, it also comes from Taylor series. So initially I will be showing for only 2 variables here for Taylor series, and you can then extend to n variables. So the Taylor series in two variable function, it is given in this way: f of x plus delta x and y of plus delta y is equal to f of xy plus delta x into del f by del x plus delta y into del f by del y plus 1 by 2 factorial into del x square plus del square by del x square plus 2 del x del y del square by del x del y and del y square by del square by del y square. Now we arrange these terms in matrix form. So left hand side is same, the first term will be same. Now we take delta x and delta y common. If we take delta x and delta y common and we write this two terms in matrix formation, it will get, we can write this in this way. It is multiplication of two matrices, and one matrix is a vertical matrix, other is a horizontal matrix. One is a row matrix and other is a column matrix. And last term, this term is written in this way. So when we have written this way, there will be one term that comes in between, that is the partial derivative term. So this term is called the Hessian matrix. So in the single variable, we directly got the that when n is odd, we got n is even, we got directly del square f by d square f by, that is f double dash of x. So d square f by dx square. So but in multivariate optimization, we will have a Hessian matrix where the function it has second derivative or second derivative with respect to the all the n variables, or here in this case only two variables. So based on the nature of the Hessian matrix, we will have a minima, maxima, or an inflection point. So it is a positive definite. If its Hessian matrix is positive definite, then x star is a relative minima. If Hessian matrix is a negative definite, in this case x star is a relative maxima. And it is, if it is neither positive nor negative definite, then x star is neither a minima nor a maxima. So this was the Hessian matrix for two variables. If we are extending it to n variables, so we will be writing the Hessian matrix in this way. So just remember how to write. So the first column will be del square f by del x1 square, then del square f by del x1 into del x2. So the first variable will be same, del x1 x1, del x1 x2, and dot 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 x1 xn. Similarly, for the second row, remember del square f by del x1 here x2 will be the common variable, del x1 into del x2, second term will del x2 square, similarly up to del x2 into del xn. Similarly for the nth row. In this way we get the Hessian matrix. So now we define, how do we define a positive definite and a negative definite matrix. So we told if the Hessian matrix is positive definite, then it is a minima. So how do we define it's a positive definite? So one standard way of deriving saying that a matrix is positive definite is by saying that if we multiply the matrix with one point in the domain, like we take any point in the domain where f of x is defined, f of xy is defined, and then we multiply by y transpose into this del square f of x of t, del square f is the Hessian matrix, and into the y. So if this is greater than 0, it is called the positive definite matrix, and if this is less than 0, then it is a negative definite matrix. But this is not a convenient way of analyzing if a matrix is positive definite or negative definite. So there are other ways which are used to get the positive definite or negative definite. The one of the most common ways is using eigenvalues. So now we have the matrix, it is a square matrix we know, and for a square matrix we can always have two eigenvalues, like we can have the eigenvalues. So we will find the eigenvalues, and if the eigenvalues are greater than 0, all the eigenvalues are greater than 0, then it is a positive definite matrix, and if the eigenvalues are less than 0, then it is a negative definite matrix. I hope you know about eigenvalues. I am expecting that. since these are taught in class 11 and class 12. And a third way is to define a positive definite and negative definite matrix is using principal determinants. So it is a Hessian matrix is positive definite if all the principal determinants are positive. So how do we define principal determinants? Principal determinants are like, this is the first term is the first principal determinant, then taking the second square is the second principal determinant, taking the third term is like that, and finally the n till the n term is the n principal determinant. If we find the determinants of all the square matrices inside the Hessian matrix, and if all the determinants are positive, it is called the positive definite matrix. And if the principal determinants are all negative, then it is called the negative definite matrix. And if one is positive and other is negative, then it is an inflection point. So in that case, we cannot say it's a minima or a maxima. So I hope this is clear. I think these are some thought. All this has already been taught in class. So before proceeding to do some problems, I will just give a basic introduction to linear programming. So I told in the first, while discussing about operations research, I told about there are different methods for solving optimization problems. So one of the methods is linear programming. So in linear programming, what is the main theme? The main theme is that the objective function, the constraints, and the decision variables, everything is linear. There is no non-linearity in the optimization problem. So here you can see, if you are taking a multivariate optimization problem, the function will be a linear function. There are n variables x1 to xn, and the first and foremost condition is all the variables should be greater than 0. That is, the decision variables should be greater than 0. And the second thing, we define an objective function, and in a standard problem we define the objective function as a minimization problem. We don't define as a maximization problem. If we have a maximization problem, we will convert it to a minimization problem by taking a negative sign in the in front of when multiplying with multiplying the objective function with a negative sign. So if you are minimizing that, then obviously you are maximizing the problem. So the standard way is to minimize the objective function. The objective function is linear. It is a like a linear superposition of n variables with multiplied by some constants c1 to cn, and it is subject to some constraints, and these constraints equations are also linear. So this is, in a typical problem, there will be n variables and there will be m constraints. So m constraint equations and n variables, it is x1 to xn. So this can be written in terms of a matrix form. We can just write the problem is f of x equal to c transpose of x. That is the first problem, subject to ax equals to b. This is the constraint, and x greater than equal to 0. These are the decision variables. So in the standard problem, the constraints are all equality type. So if we have some inequality type of constant, we will try to convert that inequality constant to a equality constant. So if we have a less than equal to type of inequality constant, we will add one variable, and we will add one variable and make that equation equal to 0, and this variable is called a slack variable. And if it is greater than type of inequality constant, we will subtract one variable and we will get the surplus. That the subtracted variable is called the surplus variable. And third case is if one variable is suppose we have defined all the variables should be greater than equal to 0, but we have one variable that is unrestricted in sign. Their sign doesn't matter. In that case, we can write it as a difference of two variables, that is xj equal to xj dash minus xj double dash. So depending on these two sign of these two variables, like difference of these two variables, the sign of xj will be greater than 0 or less than 0. So this is a basic minimization type of problem, and in this case we have told that there will be n variables and m constraints. Now if one thing is, if m is greater than n, that is number of equations is greater than number of variables, in that case what we do, we will be having m minus n redundant equations. So these m minus n redundant equations, these equations can be eliminated from the problem, and you can solve the problem on the remaining equations. The remaining equations that remain are called the pivot equations, and the other equations are redundant equations. And if m equal to n, we will have a unique solution or no solution. If m equal to n, we will have unique oblique no solution. And third case is, if m is less than n, in that case it is a case of undetermined set of linear equations. There may be of innumerable infinite solutions. So this is about linear programming, and there is also something called the basic solution. So in basic solution is one where, this is basic definitions, so is one where n minus m variables are set to 0 and a solution obtained for m number of variables. So, and the collection of the variables that are not set to 0 are called the basis. So yeah, so the other details and the problems of linear programming will be covered in the second week. So we will be today we will be solving some problems for based on the introduction part and the classification and the classical optimization part. Okay, let's see the first question. I hope this is. So yeah, the stationary points for the function f of x equal to 2x cube minus 3x squared minus 12x plus 4 are. So we have f of x equals to 2x cube minus 3x squared. So to find stationary point, what was the primary condition? Primary condition was that f dash x equals to 0. So we'll find f dash x. What will be f dash x? It will be first derivative. So it will be 6x squared minus 6x minus 12, and this is equal to 0. So this implies x squared minus x minus 2 equal to 0. We will take x squared x minus 2 into x plus 1 is equal to 0. So the values of x is equal to 2 comma minus 1. So the stationary points are 2 and minus 1. And now let us, for seeing if it is a maxima or a minima, what we have to do, we have to get the second derivative. So f double dash x is equal to we'll get the double derivative from this equation. So we'll get 2x minus 1 is equals to 0. No, sorry, 2x minus 1. It will be 2x minus 1. So this is the f double s x. Now for x is equal to 2, f double dash x is equals to 3, and for x is equals to minus 1, f double dash x is equals to minus 5. So this is greater than 0 and this is less than 0. So if it is greater than 0 at 2, so it will be a so if it is greater than 0, it will be a minima. At 2 and maxima at 1. So the correct option is option 4, a local maxima at x equal to minus 1 and a local minima at x equal to plus 2. So I think this is clear. This is like basic, whatever I have taught, I am just trying to solve that only. Any doubts in the solution?
The maxima at 1 or maxima at minus 1?
Sorry, maxima at minus 1, sorry. Thanks for clarification, sorry. Okay, I hope this is clear. So the second problem is a distinctive feature of our linear LP model, linear programming model, is that the relationship among all the variables is linear. We have shown that all the constraints, the objective function, everything is linear. So it is option A. And third question is, these are basic questions and basic concepts. While solving a linear problem graphically, the area bounded by the constraints is called the, so it is called a feasible region. So it's like that. So you have a problem. We have first seen that the variable, if we are taking only two variables, the first thing is that we will be having only this region, because x is, we have seen that all the variables should be greater than 0. So this is the part where x is greater than 0, and this is the part where y is greater than 0. Now we suppose we have a function called c1x plus c2y. So the function, the objective function can take different values, but it will be subject to some constraints. So one of the constraints is, suppose this line like this, and the other constraint is this line like this. There are two constraints. So this shaded area that falls inside all the constraints is called the feasible region. So this is graphically shown. The area bounded by the constraints is called the feasible region. The other parts, that is outside the area, outside the constraint region, is called the infeasible region. Then next problem. The necessary condition for a Taylor series expansion of f of x is that the necessary condition is f of x should be continuous and differentiable. So we have seen that f of, how it is, Taylor series is defined. Taylor series is defined as f of x plus h into f double f dash of x plus square by 2 factorial. So we have, so the thing is that first of all, It should be continuous. If it is not continuous function, then we won't have the f of x will not be differentiable at all the points. So f of x should be continuous, and if it is continuous, it should be differentiable at all the points, so that we can get n number of derivatives. So this is the necessary condition for getting a Taylor series expansion of a function f of x. Okay, so now next few questions, question number 5 to 7, I think. Yeah, question number 5 to 7 will be based on only based on this equation. It is given f of xy. It is a function of two variables is given, is equal to 100 of 1 minus x square whole square plus 1 minus x of whole square. The gradient of function f of xy is not equal to 1 comma 1 is, so if we have to find the gradient, this is a two variable function, so the gradient will be terms of two variables, that is we have to get the partial derivative of x, that is del f by del x, and then del f by del y. So we'll get, and these two terms together will form the gradient. So first is del f by del x. How do we get? So if we differentiate this function, so it will be 100 into by del x into square whole square plus del x into 1 minus x square. So it will be 100 into, so if we are using a chain rule for differentiation, 100 into 2 into y minus x square, and it will be minus of 2x plus del by del x equal 1 equal to, one second, sorry, this is not 1 minus x square, this is 1 minus x whole square, sorry. So 1 minus x whole square, so it will be 1 minus x into minus 1. So now it is given that we have to find the function at x equal to 1 comma 1. So x not equal to 1, y not equals to 1. So if we substitute here, it will be 1 minus 1 is 0. Here also 1 minus 1 will be 0. So del f by del x is equals to 0. So the second term is del f by del y. So it will be equals to, okay, again similarly 100 into 2 into y minus x square, and by chain rule it will be 1, because del x square by del y is equals to 0, and plus 0. Now the second term doesn't have any y component, so it will be 0. Now again here, if we substitute y equal to 1, x equal to 1, we will get 1 minus 1, which is equals to 0. So the gradient of the function at x not equal to 1 comma 1 is 0 comma 0. It is the first option. Okay, so now we have to find the determinant of the Hessian of the function. So we at x not equal to 1 comma 1. So what are the terms of Hessian matrix? In there are 4 terms. First is del square f by del x square. So del square f by del x square, we got del f by del x. So del f is equal to del by del x into, so how do we do this? So it will be del by del x into, we have del f by del x from this equation, so we'll substitute that. It will be minus of 400 x into y minus x square minus of 2 into 1 minus x. So we take del by del x. If we take del by del x, it will be, again I will do a variable separable, so it will be I think 400 into y minus x square into minus 400 into x into I think minus 2x, and the second term will be I think plus 2. So I think it at 1 equal to 1, so if we substitute 1 1 here, this term will go to 0. The second term will have, so it will be x equal to 800 plus 2, 800 2 I think, yeah. Okay, so this is the first term. Now let us get the second term. Second term is del square f by del x del y, or you can also write del y del x. So we'll be doing the same thing here. We will interchange del y del y into del f by del x. So it will be del by del y into minus 400x into y minus x square minus 2 into 1 minus x. So only first term will be remaining here. So since it is a, since the for x is independent of x, so independent of y, so minus 400x will come out of derivative, and in this del by del of y minus x square will be 1, and the second term will be 0. So this is equal to minus 400 since x equals to 1. And thirdly, the last term will be del square f by del y square. Del square f by del y square will be, we already have del f by del y, so it will be del by del y into 200 into y minus x square. So I think it will be 200 will come outside the derivative, and del by del of y minus x square is equals to 1 into 200. I think I did some yeah, sorry, here I have directly substituted minus 1. Two into 1 minus x, I received minus 1 only, this is fine. Okay. So the Hessian determinant of the Hessian matrix will be given as 802, it will be I think minus 400 into n, finally 200. So I think if we do the calculations, so I think this is the 400. Yeah, so the correct answer is option D, 400. This is the determinant of the Hessian matrix. Now we have to find the summation of the eigenvalues of the function. So eigenvalues of the Hessian matrix. So how do we get that? So we have this Hessian matrix. We will get Hx is equal to lambda x. So lambda is the eigenvalue. So how do you find the eigenvalue? Which is determinant of h minus lambda is equals to 0. So how in that case we will be having h02 minus lambda minus 400 and 200 minus lambda is equals to 0. Okay, wait, I will just add one page here. Okay, to get the eigenvalues of the matrix. So get the eigenvalues, which is the typical equation h into x is equal to lambda into x, where lambda is the eigenvalue. So we can, so if we reframe this equation, it will be h minus lambda I into x is equals to 0. Now, so in that case, if we have to satisfy this equation, then to get a solution, it will be determinant of h minus lambda I is equals to 0. So we will substitute the values here. H is equals to 802 minus 400 minus 400, 200 minus of lambda 1001. So the determinant of 802 minus lambda minus 400 minus 400 is equal to 0. I hope this is clear. This is like how to find eigenvalues. Sorry, 200 minus lambda. So minus 16 minus 802 minus 200. So the equation lambda square minus Okay, this is a quadratic equation, and we know for that it will have two roots, lambda 1 and lambda 2, and by property of quadratic equation, the sum of the roots is lambda 1 plus lambda 2 is equals to minus of b1, that is equals to 1 0 0. So the correct answer is the sum of the eigenvalues is 1 0 0 2. I think this is the basic algebra only, just finding the determinants and then getting the quadratic equation. So okay, now I'll proceed to the next question. It is like similar to this, just little bit addition on that. If you have any doubts in this question, you can ask now before proceeding to the next question. Okay then, yeah, if there are no doubts, I will proceed. So this is also a similar kind of problem. We have to find the Hessian matrix, then eigenvalues of the Hessian matrix, and to define if see if the Hessian matrix is positive or negative definite, and you have to identify if it is a function that f of x1 x2 is a concave function or a convex function. So before going into details, I will just define what is concave and convex. So a convex function is where they are like, if it is defined between 2 points, so in the between 2 points there will be a minima between the 2 points. And a concave function is where if the function is defined between 2 points, in between the 2 points there will be a maxima and there will be no inflection point in between. So it's a typical concave function, and a convex function is how it is defined. So in a convex function, we will always have a minima. In a concave function, we will have a maxima. Just remember this. This is because this will come a lot of times in subsequent classes. So like first question, okay, we will have the function. We will just try to solve it. x1 x2 is equals to square whole square plus x2 minus 2 whole square. So in the Hessian matrix, we have to define a determinant of the Hessian matrix. Before finding determinant, we need to find the what is the terms of the matrix. So the first term is del square f by del x1 square. So let's find before going to take, we will first find the first derivatives. Del f by del x1 is equals to 2 into x1 minus 1 plus the second term will be 0, and del f by del x2 is equals to first term will be 0, derivative of first term will be 0, second term will be 20 into x2. So yeah, okay, so now let's get a term of the Hessian matrix. So first term is del square f by del x1 square. So derivative of this term, so it will be 2. Del x1 by del x1 is equal to 1. The second term is del square f by del x1 del x2, which is equals to del square f by del x2 del x1. Similarly, so del by del x2 into 2 into x1 minus 1, which is equals to 0. And last final term is equals to del square f by del x2 square, so it will be 20, right? Yeah, del x2 by del x2 is equal to 1. So the Hessian matrix will be 2 0 0 and 20. Now what is the first question that is asked? That is determinant of the Hessian matrix. So determinant of H is equals to 2 into 20 40. Now second, product of the eigenvalues of the Hessian matrix. Okay, product of the eigenvalues. First we have to find the eigenvalues. So to get the eigenvalues, how do we do? Again, 2 minus lambda 0 0 20 minus, I'm just not using all the steps. I defined all the steps before. In this case I'm directly taking the determinant, how to find the eigenvalues. So this implies, I think, lambda minus 20 into lambda minus 2 is equals to 0. So lambda is equals to lambda 1 equal to 20 and lambda 2 is equals to 2. So product of the eigenvalues is lambda is equal to 40. So product of the eigenvalues is 40, determinant is 40, the third term. So both the eigenvalues are positive, so it is a positive definite matrix. And then number 4, if it is a positive definite matrix, we have got defined that it will be a minima, and if it is a minima, it will be a convex function. This is how it is defined. Few more problems, then we'll again this is a similar question. Here also we have to find the Hessian matrix. Okay, first we'll just quickly get the values. Del f by del x is equals to 2 into x minus 3y. It's 2 into x minus 2y. Del f by del y is equals to 2 x minus 3y into 2 into minus 6 plus of minus 4 into x minus 2y. So again, first term del square del x square. So we'll take again partial derivative of this with respect to x. So it will be 2 plus 2 is equals to 4. Second term del square f by del I take derivative of this with respect to y minus 6 plus 4 equal to minus 10, and the third term is del square f by del y square. And if we take this, I think it will be 6 3 0 18 26. So the h will be is equals to 4 minus 10 into 26. So I think, yeah, option D, 4 sorry, not for option D, it will be option A, 4 minus 10 and 26. So eigenvalues of the matrix, again you can, while doing the shortcut, I won't be going too much into the numerical details. The square minus b square minus 4 square minus 4ac by 2a equal to 30 plus minus under root 4 by 2. If we find a solution, I think it will be option D, 0.130. I am not going into details, it is like the simple calculations only. You can do the calculations yourself. So now all the eigenvalues is positive, so the Hessian matrix X positive definite. So this is solution. There are final two problems. The values are for a, or for which is a function 2x square plus 2xz plus 2ayz plus 2z square will be concave one. So we have to find the value of a for which the function is concave. Okay. So if it is a concave one, then it should have a maxima, and if it is a maxima, what are the conditions? F dash x is equal to 0, f double dash x is less than equal to 0. So let's first find f dash x. So in case of f dash x, you have to, we have to do first to get a partial derivative. Del f by del x equals to 4x plus 2z first equation is this one. The second equation will be coming del f by del y is equals to 0. So del f by del y will have 2az is equals to 0. The second equation, and third equation is del f by del z is equals to 2x plus 2ay plus 4z is equals to 0. Now we have three equations. The thing is that we have three equations and we have four unknowns, right? X, y, z and a. So if we have four unknowns, we'll need one more equation. So we'll get one from the Hessian matrix. So one possible solution for this equation is like in this equation. So here the z can take any value. It is an arbitrary value. It is not necessarily 0. So if the z can take any value, and we have to see that del f by del y, it has to be 0. When del f by del y is equals to 0, in that case the z can take arbitrary value. So it can be 0 always when 0, like in case of a maxima when we have a is equals to 0. So one possible solution is a is equals to 0. Now at a is equals to 0, how will the Hessian matrix be? So let's substitute. In that case f of x is equals to in that case we can substitute the f of x is equals to 2x square plus 2xz plus 2z square. So in this case, how if we take the f del square f by del x square, so what will it be? So it will be 4, and I think this will be 0 and the other two terms will be 0. Second thing, second term will be del square f by del x del x del z. So this will be we have del f by del x. If we take with respect to del z, it will be 2, and third term is del square f by del z square. So here a is 0, 2x is 0, so it will be 4. So the Hessian matrix will be 4, 2 to 4. So now if we take the eigenvalues, 4 minus lambda into 4 minus lambda minus 4 is equals to 0. Lambda square lambda plus 12 is equal to 0. 6 comma 2. Eigenvalues are positive. Now if a is equals to 0, it should be negative definite if we have it's a negative definite if we have the eigenvalue is negative. Yeah. So thing is that at a is equals to 0, the lambda values are positive, so in that case it will be a convex function only. I don't think it will be a concave, so I think there is some
So
discrepancy.
lambda square minus 4 lambda plus 12 it should be, sir. This addition you see, sir. Lambda square minus 8 lambda.
Yeah.
8 square lambda square minus 4 lambda it seems, sir. 16 minus 4 it becomes 12, sir, here. This will be 4 lambda.
Why 4 lambda?
Lambda square.
4 minus lambda, 4 minus lambda, we have this one, na? It is
Okay.
lambda minus 4 whole square. So it lambda minus 4 whole square is lambda square minus 8 lambda plus 16, right? And 16 minus 4 is 12.
Okay.
You got it? So this is the square. If you expand this, it is like lambda square minus 8 lambda plus 16, right?
Yes, sir.
And 16 minus 4 is 12. That's what I wrote directly. That's I think yes. Okay, we'll see to it again. Let's see the next question. After that, we will see this again. If or else if I tell in the next class if there is some discrepancy in the result. The next question is again a similar kind of question. F of xy is equal to x squared minus 4a 5y squared. So it will be concave for this thing. I think if they are defining concave as the for minima, then I will be clarified. Okay, we'll solve this question and then see. First, I will take the derivative of del f by del x is equals to 0. One second. Okay, so yeah, we'll get the derivative. So we'll go to a definition of concave. So del f by del x, we're not taking a 0, we're just getting the function initially. So what will be del f by del x? It will be 2x minus 4ay. Yeah, I think 5y square is 0. And del f by del y is equals to 10y minus 4ax. Now, by definition of concavity, it a function is concave if its derivative is strictly or monotonically decreasing. So this should be monotonically decreasing. So how do we get a monotonically decreasing kind of function? So we'll have to find the double derivative, del square f by del x square is equals to 2 del y square is equals to 10, and del square f by del x del y, and del square f by del x del y, it will be equals to minus 4a, right? So yeah, so if we take the Hessian matrix, it will be 2 minus 4a and 10. So if it is 10, now let us take the one more thing we discussed, that the determinant, that is all the principal determinants should be positive for minima, that is principal determinants 1 is 2 and is the whole determinant, and the principal determinants are negative, then it is a maxima, that is a okay. We will see what is the principal determinant here. So determinant of h equal to 20 plus minus 16 a square. So this principal determinant so it will be 0 if a is equals to under root 20 by 4. Now if a is greater than under root 20 by 4, if a is greater than under root 20 by 4, then 20 minus 16 into a square. So this value will be greater than, sorry, it will be less than 0. In that case, h determinant s is less than 0. This is one thing. Or else if a is less than root 20 by 4. In this case also 20 minus 16 into a square. This a square will be greater than 20 by 16, so this whole term will be less than 0. So determinant h is less than 0. So the function, for the function to be concave, we'll have to get this the value of a, that is a should be greater than root 20 by 4, or a is less than equals to minus of, sorry, this is not plus, minus of root 20 by 4. In that case, determinant of Hessian matrix is less than 0, and we'll get negative definite matrix, and if it is negative definite matrix, we will have a concave function. Okay, so this is clear for this question. Okay, for the first question, okay, then we'll go with the three terms, the three ordered 3 by 3 matrix, and we'll see that if we can get some insight. Okay, we have del f by, so we'll find all the other terms. Del square f by del x square is equals to 4. Del square f by del x del y is equals to 0. Del square f by del x del z is equals to 2. For the second term, del square f by del y square is 0. Del square f by del y del x is 0, and del square f by del y del z is equals to 2a. And for the third term, del square f by del z square is equals to, I think, 4. Del square f by del x del z is equals to 2, and del square f by del z del y is equals to 2a. So let's have the Hessian matrix. We will have the Hessian matrix in the Hessian matrix is this term 4 0 2 0 0 2a 2 2a, and finally 4. I think am I correct? Or the order x y z x y z, yeah. So let's find the determinant of the Hessian matrix. So it will be 4 into minus 4a square plus 0 plus 2 into 0. Okay, so it will be 16 minus 16 a square. Now, yeah, in this case, whatever be the value of a, so this determinant h will be negative only. If a is 0, in that case if a is 0, in that case determinant h is equals to 0. Now for having a concave function, he can take any value actually. If he takes any value, even so this is negative only. I'm not doing any mistake, right? The order is it is monotonically decreasing for all values of a, so but it has to satisfy this condition also. Okay, based on the Hessian matrix, I think it is possible for all values of a, but for this second condition, that del f by del o is equals to 0, so this function doesn't depend on y, it depends only on a and z, and this is will be 0 for all values of for y if a is equals to 0 only. I think that is the explanation. So that is why we are going only with one solution, that is a is equals to 0. Anyways, yeah, that was all for today. I think I have covered some problems. If you have any doubts, you can ask me now.
So you'll be giving the recorded section of this video, sir?
Yeah, sorry.
You'll be providing this recorded section of this video?
Yeah, I will be uploading this in the YouTube, in my YouTube
Thank you.
channel, and I think you will be provided with that by the NPTEL, the recorded video in my YouTube channel, okay, and with the PPT and the slides, everything. This will be shared with you. No, don't worry about that. So yeah, anything else to discuss? If there's nothing, we can end the meeting, or if you have any doubts, you can also ask in next. I go to the video once again. You can also ask in next class also. Okay then. Yeah, if there are no doubts, we will close the session for today. Okay. Have a good day and have a good night. Thank you for all for attending.